Hello, my name is Shane Hamilton, and for my solid state project I've chosen to cover carbon nanotubes. For the purpose of this project I've divided this topic into the following headings. First of all, I'll do a brief introduction, followed by a really brief history. Then I'll outline the structure, the properties that arise from the structure, and how we go about creating nanotubes, applications, and then finally a really short conclusion. What are nanotubes? Basically they're rolled up sheets of graphene enclosed at the end. They typically have a diameter of 1 to 30 nanometers. They have an incredible length to diameter ratio of 132 million to 1. They have really incredible properties which include electrical conductivity, strength and elasticity, thermal conductivity, field emission, high aspect ratios. Really exciting applications for the future. Recently they've attracted loads of attention, many papers being published each year and increasing amount of investments. A large number, there's still a lot of technical difficulties overcome, particularly with regard to production costs. It's not really commercially viable, although there are a few companies that sell sporting goods like tennis rackets and bikes. But once the cost of processing comes down, it should take off. A really brief history. In 1950, two Soviet scientists showed it's possible to create hollow graphitic carbon fibers. 1960 then, a paper appeared in Nature, the scientific journal, on the friction properties of carbon due to rolling. Then in 1976 a method was developed for creating carbon fibers. In 1987 fullerenes were discovered. Fullerenes are carbon structures that are basically hollow. This is when carbon nanotubes really took off then as a concept. 91 the arc discharge method was developed for the first time. 93 single wall carbon nanotubes were created. They used transition metals like cobalt, nickel and iron. 95 Swiss researchers showed the incredible electrical properties. 2001 then, the first technique for separating semiconducting and metal nanotubes was found. This can be really useful in microelectronics. Then in 2002 it showed that multi-walled carbon nanotubes were the fastest oscillators they'd ever recorded. And then last year IBM was able to create a transistor that outperformed its equivalent silicon transistor. The structure is really very basic. The carbon atoms of the single sheet of graphite form a planar honeycomb lattice. Each atom is connected by a really strong hybridized sp2 bond to three of its neighbours. This is the source of its strength. It's graphite sheets that are rolled. The way it's rolled determines what type of nanotube it's going to be. Armchair, zigzag or chiral. An armchair and zigzag, they're really symmetrical, not as common as chiral. See, armchair refers to this type armchair shape here, and the zigzag equivalent here. The chiral has mirrored symmetry, and the chiral is really the most impressive one because it has incredible electrical properties. The structure of a nanotube is defined by integers n and m. To say create a nanotube with 6 tree, you take one half the first tube, label an atom 0, 0 and superimpose it on the second tube, the atom labeled 6, 3. If it's a zigzag, the m will always be equal to 1, and if it's an armchair, n and m will just be the same. There's three main methods of synthesizing carbon nanotubes. The first and most common is the arc evaporation. It produces really high quality carbon nanotubes, but it's actually quite expensive and only really done in labs. The second is the more industrial friendly. It's the catalytic synthesis methods. There's a few of these. They have a high yield but poor quality if it's relatively cheap though. The final method uses, it's the arc evaporation, but instead of using current it uses a laser. It's a bit cheaper, but it's still not as cheap as the catalytic synthesis. The arc evaporation passes a current of around about 50 amps between two graphite electrodes in an atmosphere of helium. The graphite vaporizes and then condenses on the walls of the reaction vessel, but some of it condenses on the cathode, and the carbon that condenses on the cathode forms some carbon nanotubes. You can create single wall carbon nanotubes if you use cobalt or nickel, and in the anode you can also use iron. The synthesis. This has been known since the early 50s. It's most probable to be scaled up to an industrial level. The carbon nanotubes can be made by passing carbon-containing gas, such as CH4, over catalyst. Catalyst is usually a transition metal. The metal catalyst catalyzes the breakdown of gaseous molecules into carbon, and then a tube begins to grow. In 1940, they showed it's possible to make single-walled carbon nanotubes. The final method is just the arc evaporation, but with a laser used to vaporize the carbon instead of the current. It's got a high yield and it's relatively good quality, but it's not as cheap as the catalytic synthesis. The properties, well, the main properties, the most impressive rather, are the electrical conductivity, thermal conductivity, expansion, its strength and elasticity. It has great field emission aspects and a high aspect ratio. The electrical conductivity, it can be incredibly conductive, more conductive even than copper. This really depends though on the way it's formed, how its chirality really. It enters N and M. The conductivity is a function of chirality. The multi-walled carbon nanotubes behave differently to the single-walled carbon nanotubes. The multi-walls are better conductors, but their inter-wall reactions can be found to distribute the current over individual tubes in a non-uniform fashion. The single-wall carbon nanotube don't have this problem, but in the ropes the current can change abruptly at various positions. It typically has a current density of 107 amps per centimeter squared, but theoretically it should have a density of about 1013 amps per centimeter squared. This is because in practice it isn't as perfect as in theory. The resistance is 10 ohms per centimeter at 27 degrees Celsius. Also, below 27 Kelvin it should behave as a superconductor. It's the most conductive fibre known. It may contain defects, but these defects are actually useful because they enable us to create transistors, which are very useful in molecular electronics. Carbon nanotubes at natural junction behave as a rectifying diode, and they've been shown to be the fastest oscillators to a speed of 10 gigahertz. Elastic modules and graphite, one of the largest in the world. The basal plane elastic modulus of graphite is one of the largest known of any known material. For this reason, carbon nanotubes are stiffer than steel. It could be 100 times stronger than steel. They're very resistant to damage. If you built a probe of carbon nanotubes and if you press the tip, it would bend and return, but no damage would be done. It's incredibly useful in biomechanics. It has a Young's modulus of about 1 terapascal, which is really unmatched. With regard to the thermal conductivity and expansion, it's recent research has shown it's probably one of the best heat conductors known. This would be incredibly useful for heat sinks in molecular electronics. They're shown to be superconductivity below 20 Kelvin. The strong carbon-carbon bonds, it really means that if you heat it up and cool it down, not too much damage will be done. It's really resistant. Regarding the field emissions, this is because basically it's got such a narrow tip. It really is a brilliant emitter of fields. fact, they're actually one of the best known field mirrors of any material. This is their high electrical conductivity and their incredible sharpness of the tip. It's a smaller tips radius of curvature, the more concentrated the field will be. It's the same reason that lightning rods in the sky are sharp. The sharpness of the tip also means that they emit at especially low voltages, which means you can build much lower voltage devices. Carbon nanotubes represent a very small, high aspect ratio conduct active plastics. So recently plastics have been replacing metals, and they're incredibly good structurally, but they don't really carry charge. So to counter this, you can introduce substances that can carry charge. Carbon nanotubes are perfect because they're relatively light, and because they're high aspect, it means that a lower loading, a concentration of carbon nanotubes is needed compared to other conductive additives like metals, which will be much heavier. Finally, here we have the applications. With regard to thermal conductivity, like besides the obvious of building buildings or in electronics, you can build heat sinks and make dramatically smaller devices. Field emissions, that's really nearly a military application for absorbing and emitting radar signals. Conductive plastics, again, that's just seen already. You can introduce these new tubes to plastics to make them conduct electricity. You can also perhaps even use them in more scientific application of solar panel paint. They've been shown to show great energy storing capacity because they're incredibly strong, obviously, but then also with regard to fuel cells. Molecular electronics means you can make much smaller devices that run in much lower voltages, and also the heat sink means that it won't heat up as much. Structural composites, which is probably the most obvious use, is building substances that are incredibly strong. One of the most far-fetched idea is the space elevator. Fibers and fabrics then is clothing. This is another military application with regard to bulletproof vests. Then there's catalyst support. In biomedical as well, they're not sure yet if carbon nanotubes are toxic or not, but if they weren't toxic, they could be used a whole host of applications, from support to delivery of medicines. And finally, in conclusion, due to its unique structure, it has incredible properties. It really an incredible substance. It's not really cheap. Like, the next big thing has to come now is developing a cheap method of processing. Once that's done, then you've boundless applications. One, again, most far-fetched is this space elevator. But it may be a good few years before we see them commonly around. You'll probably be at Mars before we see anything like a space elevator. Maybe another 10 or 15 years before it replaces other metals. Thank you for listening. My name is Shane Hamilton, and this is my project.